We continue the evening part of lecture 4. We see the topic Laplace transform of derivatives. Now for this we take the theorem. Let f of t be continuous. Let f of t be continuous for all t greater than equal to t for all t which is positive, for all t which is positive, and f dash of t be piecewise continuous f dash of t be piecewise continuous on every finite interval, on every finite interval in the range t is greater than equal to 0. Also, let f of t be of exponential order so that there exist constants m alpha t such that mod of f of t less than or equal to m into e to the power alpha t, since the function f of t is of exponential order, for every t greater than t. Then Laplace transform of f dash of t, exists, and it is given by Laplace of f dash of t equal to s into Laplace of f of t minus f of 0. This Laplace of f of t we can write it as f of s. Therefore, s into f of s minus f of 0. Laplace of f dash of t equal to s into Laplace of f of t minus f of 0. We prove this theorem. Prove. We use the definition of Laplace transformation by definition of Laplace transform. We have, now you know the definition of Laplace transformation. Laplace of f of t equal to integration 0 to infinity e to the power minus st f of t dt. Laplace of f of t equal to, the definition is integration 0 to infinity e to the power minus st f of t dt. Now we have to find Laplace of f dash of t. We have to prove this formula. Therefore, in place of f of t, we replace the function f of t by f dash of t. Therefore, Laplace of f dash of t equal to integration 0 to infinity e to the power minus st f dash of t dt. Now we integrate this right hand side by doing the integration by parts by LIT rule. Integrating by parts, taking e to the power minus 60 as the first function, and f dash of t is the second function. F dash of t means derivative of f of t. Therefore, integration of derivative, we have the original function f of t. Therefore, using the formula for integration by parts, we get first function e to the power minus st into integration of second, integration of derivative, we get the original function f of t, and limits from 0 to infinity, minus integration of second function, again integration of f dash of t, f of t, into derivative of first function with respect to t, derivative of e to the power minus st, e to the power minus st into minus s. We take the derivative corresponding to t. Therefore, the upper limit is infinity, lower limit 0. Therefore, limit t tends to infinity, upper limit e to the power minus st f of t, lower limit 0. Therefore, lower limit t tends to 0 e to the power minus st f of t. Now here the minus s, taking outside the integration, minus of minus plus s, integration 0 to infinity e to the power minus st f of t dt. Now this term is by definition of Laplace transform. We have integration of 0 to infinity e to the power minus t f of t dt is nothing but Laplace of f of t by definition of Laplace transformation by equation 1. And here the integration of this is limit of this is 0 because it is given that the function f of t is of exponential order, but f of t is of exponential order. Therefore, we have limit t tends to infinity e to the power minus st f of t equal to 0. Therefore, we have equation 2 implies Laplace of f dash of t equal to the limit of first term is 0 minus here t tends to infinity, t equal to 0, we take this e to the power minus st in the denominator, we have e to the power st, that is 1 upon e to the power st, t equal to 0, therefore 1 upon e to the power s into 0, therefore 1 upon e to the power 0, e to the power 0 1, therefore we get 1. Therefore 1 multiplied by f of 0. And this is nothing but by definition 1, by definition of Laplace transform, we have this as s into Laplace of f of t. C is by definition of Laplace transform. Therefore, we could get Laplace of f dash of t equal to s into Laplace of f of t minus f of 0. The theorem is proved. Now second we prove the formula Laplace of f double dash of t, it is given by s square into Laplace of f of t minus s into f of 0 minus f dash of 0. That is, we can obtain this formula by using the first formula. Here the right hand side is multiplied by s, therefore here s square into Laplace of f of t minus s into f of 0, then additional term is f dash of 0. Now here Since f of t is replaced by f dash of t, we can write here Laplace of f double dash of t equal to Laplace of f dash of dash f dash of t and dash of this. Then by using the previous formula, we can write s into Laplace of, here f of t means this function f dash of t minus f of 0. Then we use the formula for Laplace of f dash of t, that is from previous formula. Therefore s into Laplace of f dash of t, it is given by s into Laplace of f of t minus f of 0. Now here we get, here the function is f of t equal to f dash of t and dash of this. Therefore we get here the function f dash of 0. Therefore we have this f dash of 0 outside. Then multiplying by s, we get the required formula. Multiply by s, we have s square into Laplace of f of t minus s into f of 0 minus f dash of 0. This is the formula for Laplace of f double dash of t. Similarly, we can find the formula for Laplace of f triple dash. Laplace of f triple dash of t, it is given by, multiply this formula by s. Therefore we have s cube Laplace of f of t minus s square into f of 0 minus s into f dash of 0 minus, then again additional term is f double dash of 0. If there is third derivative, then here is second derivative f double dash of 0. If there is second derivative, then there is a fourth derivative f dash of 0, and so on. Now similarly you can find the Laplace of, we have four derivative. Four derivative of f of t, it is given by s to the power 4 Laplace of f of t minus s cube f of 0 minus s square f dash of 0 minus s into f double dash of 0. That is this formula of third derivative, we multiplied by s. Therefore s to the power 4 into Laplace of f of t minus s square into s into s square into s cube into f of 0 minus s square into f dash of 0 minus f double dash of 0. Additional term is there. We are multiplying by s to the power 4 s cube s square into f dash of 0 minus s into f double dash of 0. Then the last term is minus f triple dash of 0. Multiply this formula by s, we get the term, the expression like this up to this. Then the additional term is, this is the fourth derivative, therefore we have a third derivative f triple dash of 0. Now we see examples on this formula. Using the theorem of Laplace transform of derivatives, Using the theorem of Laplace transform of derivatives, find Laplace transforms of first cos 80 t sin 80, cos 80, second t sin 80. Solution. First, let f of t equal to cos of 80. Therefore, find the derivative f dash of t equal to derivative of cos 80 minus sin 80. Therefore, minus a sin 80 f double dash of t. Again, derivative of this, derivative of sin 80 cos 80. Therefore, a square cos 80. Then f of 0. Here t equal to 0. Cos of 0 1. Then f dash of 0. Here t equal to 0. Sin 0 0. Therefore 0. Then using the formula, by using the formula, Laplace of f double dash of t equal to, yes, it is given by s square into Laplace of f of t minus s into f of 0 minus f dash of 0. Now f double dash of t is given by this. Therefore, Laplace of minus a square cos 80 equal to s square Laplace of f of t, Laplace of cos of 80 minus s into f of 0 equal to 1, f dash of 0 is 0, therefore minus 0. It implies a square is outside, a square into Laplace of cos 80 equal to s square into Laplace of cos 80. We know Laplace of cos 80, s divided by s square plus a square minus s. Now, in the previous step, we have to take Laplace of cos 80 common. Laplace of cos 80 common. Therefore, inside we have s square plus a square. Then on the right hand side we have s. Therefore, we have Laplace of cos 80 equal to s divided by s square plus a square. And we know this is the formula of Laplace of cos 80, s divided by s square plus a square. You try to solve the second example. Take f of t equal to t sin 80. Now try to solve second example, f of t equal to t sin 80 by using the same formula, Laplace of f double dash of t. For this lecture, we'll stop here.